Okay, welcome to the next class on multiple view geometry. Today we'll talk about basically the second central part in the image formation process. The idea of multiple view reconstruction is that we want to invert the image formation process, i.e. we want to go back from the images to the 3D coordinates, the 3D world. And in practice, the way we do this is that we first study how our image is formed, how we get from this 3D world to the images. And then once we have fully understood that, we will aim at inverting that process and going back from the images to the 3D world. And in the last class, we talked about how to model the motion of the camera, translation of the camera, rotation of the camera. And today we will talk about the second main part in the geometry of image formation, and that is the projection of 3D points onto a 2D image plane. And that is actually the two elements that make up the geometric image formation process. One is that we get points in world coordinates into the coordinates of the current camera, and once we have them there, then we can project them onto the image plane. And this projection, there is actually a lot of different ways to project points onto a plane, onto 2D, but the most common one, the most popular approach, and in some sense simplest approach, is the so-called perspective projection. Before I get started, maybe some historic remarks to start off. Perspective projection has a long tradition in history, in sciences. It actually goes back. Some of the earliest treatises of perspective projection are by Euclid in the 4th century before Christ. So more than 2,000 years ago, humans have thought about perspective projection. And actually, partially correct perspective projections are visible in old frescoes of Pompeii even before Christ. So already before Christ, people knew about perspective projection and how to make use of it to portray at least partially correct representations of the 3D world. Something that is a bit surprising and happens frequently in history is that knowledge all of a sudden seems to be lost in the history. So there is a period of around 1,000 years, basically with the fall of the Roman Empire, where people in arts did not seem to be aware of these aspects of perspective projection. So if, for example, if you look at medieval paintings, a lot of paintings in churches and the like, all of these medieval paintings are characterized by the fact that they seem very flat. So there is no notion of depth in the images. There is no notion of foreshortening, the things that usually make up a perspectively correct representation of the world. Now, art historians will typically argue that in the medieval times this was not of interest. People did not want a perspectively correct representation of the real world, but rather some iconic, visualization of key aspects of say, the church, etc. Nevertheless, there was no perspective projection in medieval paintings, and it emerged much later in the Renaissance art, when all of a sudden artists started to kind of rediscover the rules of perspective projection and made use of this extensively in their paintings. And I'll show a couple of examples in a second. So there's famous artists like Brunelleschi, Donatello, Alberti, and there's even treatises on how the projection process works. How this is done. There's a treatise called Della Pittura by Alberti, and he demonstrates how this perspective projection works. In addition, in the Renaissance period, there's a lot of expertise that was gained about not just the perspective projection, but also about how light interacts with matter. So once light hits the surface, how do we perceive colors? How are they modulated by the lights acting on them? For example, Leonardo da Vinci did detailed treatises in the 1500s, and so also there are studies of Caravaggio and Raphael in the Renaissance paintings about light effects on and how to capture them in painting. For us, this is useful. And in fact, the Renaissance period provided a lot of insights and knowledge that can be used today in computer vision. Because once you want to invert in computer vision, ultimately what we want is we want to get from images to a model of the world, a model of the scene in such a way that if I look at this model with this illumination in these surface properties, that's the image I would get. And ideally that image should then match the observed image. And so this is the image this inversion process that we want to model, but what it requires really is a good understanding of how images are formed. And much of this was already devised in the Renaissance period. Here are some examples. This is a painting by a monk, Filippo Lippi, The Feast of Herod, Salome's Dance. And what you see very nicely is this depth, this sense of depth that you get in these paintings of the 15th century. And the way this comes about is that you have a vanishing point, a so-called vanishing point, and then lines that are parallel in the real world actually converge to one vanishing point in the image. And that, as you can see here on the floor very nicely, that these lines that are in principle parallel all seem to converge to some vanishing point in here. And that gives you that feeling of foreshortening, that aspect that things get smaller the further away they are from the camera. And so clearly Filippo Lippi had a good understanding of how perspective projection can be used to give you that sense of depth. Here's another example, the famous School of Athens by Raphael. So these are all famous philosophers arranged in this painting. But what's important for us are not the philosophers, but the fact that the depth again emerges through this foreshortening effect. Oopsie. Sorry about that. Here's another example from the 16th century, Albrecht Dürer. This is a machine that he devised to give a perspectively correct representation of a 3D object. So you have a 3D object here, and then you can imagine your camera, or the human eye, if you will, the observer, is standing right here. And so the rope that you see here is fixed here, and it makes a straight line to the point. And so basically then you put the screen in between and you say, where would this point of the object appear if I wanted to project it on the screen, if it was observed from that location? And so you have he has an assistant there who marks off the point where the rope goes, and then once he closes the lid here, he can mark the point on the screen there. So that is a manual reproduction of what a camera does today. It basically has a sensor here that just stores the brightness values. At the time they didn't have that, and so they had to do it manually. And so what you have here in the 16th century is a first kind of a machine that allows to manually reproduce what a camera does. This has been actually used in satire. Here's an example from the 18th century by a British artist, Hogarth. And what you see here is that he made use of the rules of perspective projection, but in a way that you get inconsistencies. For example, there's the lady up in the house. She's leaning out of the window with a candle, and she lights the pipe of that wanderer who actually is in the background. So although locally this is all consistent, on a more global spatial scale, there is an inconsistency in the sense that these two persons are next to one another, but we know from perspective that they're actually at a very different depths. And since this depth is not there, here's another example. This guy is in front of the bridge. He shoots in a straight line at this bird, but the bird is actually behind the bridge. So strictly speaking, they are at a very different level of depth, so they should not be able to, basically, he should not be able to shoot the bird. Or here, this guy has a fishing rod, and although he stands much closer to the viewer, is much larger, the fishing rod extends to some place behind the other guy's fishing rod. So a lot of these inconsistencies in the painting. The flag, for example, that is fixed to the building is actually hanging behind the trees in the background. So someone made use of this to kind of make fun of or ridicule the notion of perspective projection. And I guess this is not so well known, but there is much more known ways to distort perspective projection, and this I guess most of you have seen before, is a Dutch painter, artist, Escher, MC Escher, and he systematically used perspective projection and twisted it in many ways. Here, for example, you have a perspectively projected visualization that shows a good sense of depth, but the issue is that you don't have an understanding where gravity is, where is the bottom. For example, here, the bird is sitting here, so you would say this is going down, but then that bird is sitting in a way that you would say down is this way. Similarly, these horns, one is hanging this way, one is hanging the other way, so you get a lot of inconsistencies. And interestingly, in all of these drawings and paintings, locally everything makes sense, but on a larger scale you get inconsistencies. Similarly here, locally this makes sense, the stairs go up, the ladder goes up, but then if and locally, for example, this pillar goes down here, that pillar goes down here, but if you look, that pillar is in the front of this one here, and then once you go up, all of a sudden it's further behind the other one. Similarly here, the pillows are all kind of skewed. So it's quite entertaining how Escher made use of perspective projection to give you twisted representations of the world.
Can I ask a question? Is there any book about perspective projection rather than paintings from those times?
Excuse me, is there any book?
Yeah, written about projection or something rather than paintings.
I'm sure there is. I don't know whether Escher actually wrote books on this topic, but he was an artist who was very scientific in many ways, and who was very mathematical in many of his drawings. So in fact, my experience is that Escher is extremely popular as an artist among mathematicians. Let's get back to how perspective projection arises, how it can be modeled mathematically, and in practice the way perspective projection emerges is by the so-called pinhole camera. This is something I realize I don't have on the slide, so I'm going to draw it here. The simplest way to actually construct a camera, and that's been done many years ago, hundreds of years ago, is that you take a room that is dark, completely black, and then you have a little hole in the front wall, and then you have an object, say a person or something like that, and the light that is emitted from that person enters that hole, and so what you see on the back here is an inverted picture of that person. And that actually works, I've tried it. But what you have to be careful about, sorry, this of course goes through the hole. First of all, the hole has to be very small. Otherwise, this is not going to work. And this is why it's called a pinhole camera, this concept. This is the concept of a pinhole camera, because you have to have a very small hole In addition, and then it works, but the problem is, of course, if you have a very small hole, there's very little light that enters the thing, such that the object, the projection here is barely visible. So it has to be very dark, the hole has to be very small to get a correct projection. And so in practice, the object that you're looking at has to be very bright. I've tried it myself. For example, if you construct a little box and then you have a little hole and then you have a candle, for example, that you look at something that is very bright so that you still see an image of it. This is the pinhole camera. This is one of the earliest realizations of a projection on a screen, and this was used by various scientists in history as well. In practice, it's not very good, because if you want to image objects that are themselves not very bright, say in a darker room, etc., this is not going to work well. You need a very sensitive sensor. Nevertheless, there are systems, technical devices that make use of the pinhole camera because the projection is very accurate. It is the so-called perspective projection that you get. What we use nowadays is slightly different. In order to get more light into the camera, we use lenses. The idea of a lens, as you know, is that it allows to bundle light. And the way it does that is that there is something called refraction. So the lens is made up of a different material, of some kind of glass, for example. And the issue is that light travels differently inside the glass than outside in the vacuum or the air. And so that leads to a refraction. So a light ray that enters the lens in parallel to the optical axis here will leave the lens through what's called the focal point of the lens. And due to symmetry, light that goes through the focal point on the other side of the lens and enters here will leave the lens parallel to the optical axis. These two focal points that we have here, they need not be the same. But once the lens is symmetric with respect to the axis, the same thickness on both sides, typically the focal point here and there have the same distance from the lens. And so what you get in this fashion is that the rays of light that leave this point in various directions are bundled again in this point. And so if then you put your screen here, so you have a larger hole than in the pinhole camera, all this light is actually bundled here, and you then see an image of this object on that screen. So this is a way to go beyond the pinhole camera and allow to accumulate more light and to get a brighter image of an object. So the assumption is that here we have an object standing there, and here we have the image of the object on the other side.
And do we use light lens?
Yes. So this model is a model for a thin lens. In practice, lenses create all sorts of aberrations. In practice, when you have thicker lenses, we'll get to that later, but here the approximation is that we have a thin lens and then we have an essentially a perspective projection. And maybe to give you a better idea of where this approximation comes in, if you look at the lens, there is 2 points. Once the light ray enters the lens, we have one refraction happening. So it doesn't continue in a straight line, but there is an angle. But once it leaves it, there is another refraction point. And the approximation of the thin lens is that these two refraction points are essentially the same. So they're at the same location. And so in practice, we say the point of refraction is in the middle here somewhere. And this is the approximation we make. So we neglect the fact that it actually gets refracted at two slightly different points. And this approximation is valid for thin lenses, but it is no longer valid once you have a thicker lens. And so once you have a thicker lens, this is not as simple, the whole refraction process. But since the perspective projection is a fairly simple one, mathematically well understood, we work in this class with the thin lens approximation, and I'll mention a little bit later on what you do with thicker lenses. How can we derive the perspective projection equation? The way we do that is by looking at these two triangles. So one is triangle A, this one, and one is triangle B, this one here. And now you can imagine, let's say you move this point in the 3D world around, that affects the triangle A clearly, but it similarly affects the triangle B. So for example, if you move this point down a little, then the projection also moves down. It gets smaller, basically. And so what we can say is that these two triangles are similar in the sense that this length compared to that length is the same as this length compared to that length. And if we put symbols to these, let's say we call this length the length of the object in the world, that is large y, and this length we call the length of the object in the projected image, that we call small y. Then we see that, and then we call z, large z, the distance of the object to the focal point, this length here. So we see that large y divided by large z is the same as small y divided by the focal length f.
Why do we have minus?
We have a minus, indeed, there is a minus as you can see here, because one is pointing up and the other one is pointing down, right? So if I put things in the same coordinate frame, if this has a positive length, then this clearly points the other way. And indeed, when you use a pinhole camera, the image of the object is inverted. Now, interestingly, once you switch on a digital camera and take a picture, on your screen, the image is not inverted. You may have noticed. The reason is that intrinsically it just flips upside down. Why? Because then you can drop the minus sign. You can say, well, you know, it doesn't matter if we look at the image upside down or right side up, we can just flip things. And in fact, we will do that also in the mathematics. We will drop that negative sign because, you know, if you project things and then you always get minus signs, it just complicates life. And so we will just consider that the image plane is considered upside down, that things are flipped. And what that corresponds to, assume that this is the center of projection, so this is where the length is, so we actually would have our image of the object in the world, we would have it on this side, but if we flip it, it's equivalent to saying the screen is not behind the camera, but in front of the camera. So in a real physical camera, of course, the sensor, the screen or the sensor is behind the lens. But if we then acquire an image and flip the image, it amounts to geometrically saying that the image plane is in front of the lens. And so we will use this visualization for the projection process of a perspective camera. But of course, in a real camera, the screen is not in front but behind. But you can imagine these are equivalent, whether I have a screen behind and then consider it flipped, I invert the axes, or I put the screen in front, geometrically comes out to the same thing. And so this flipping of the signs to drop the minus sign is just to simplify the notation. You could as well keep the minus sign and just keep it in all the equations, but we want to make things simpler, and so we just flip the signs of x and y axis. And that mathematically amounts to putting the screen in front, and so we will work with this analogy. Here is the object, and here's the perspective projection of the object. And that perspective projection, let's see if we go back here, you can solve for the image y as a function of large y and large z, and what you see is it's large y divided by large z scaled by the focal lengths. And then, as I mentioned, we will just drop the minus sign, so this is the perspective projection. And so what you have here is the equation of perspective projection. It says a 3D point is mapped to a 2D point by scaling with the focal lengths and dividing by the z coordinate. And that is, of course, assuming that the z coordinate is in direction of the optical axis. We will assume that for now, that we put everything in the camera coordinates, and that means the z-axis of our coordinate system corresponds to the camera axis. And so this is the perspective projection. This is how to get from a 3D point large x to a 2D point small x. It's fairly simple, as you can see, but there's one thing that makes it really nasty and unpleasant, and that will occupy us basically for the rest of the class, is that this transformation is nonlinear. So to get from 3D to 2D is a nonlinear transformation, and the nonlinearity is that you divide by the z coordinate. This makes the transformation nonlinear, and this is what makes it difficult to invert. Linear transformations, matrices, I can multiply with the inverse of the matrix to invert things. If I have a nonlinear transformation, that's not going to work. And this is a problem. But for much of this class, we will try to avoid this problem, at least notationally. And the way we avoid it is that we multiply z over to the other side. So you see little x is f times large x over z, and f times large y over z, a 2D point. But if we multiply the z coordinate over, we get little x times large z is f times x. And f times y. And so we can write that in this fashion. This is using so-called homogeneous coordinates. We've seen them before. The homogeneous coordinates, basically they take a 3D point and just append a fourth coordinate, that is 1. And you remember we used that originally to include the translation in the rigid body motion. We can do the same for the 2D coordinates, so little x, little y. We can make a homogeneous coordinate vector for the 2D point. That is that vector here. And then we see that z times this 2D vector in homogeneous coordinates is nothing but this matrix times the 3D vector. And the way, I mean, clearly you see it just scales things. X and Y are scaled by the focal lengths. Z is scaled by 1, but since we then have Z here, it basically, there's a 1 in the last component. And so in that fashion, by multiplying over the Z coordinate, we have a linear, the remaining transformation is linear. And that is often useful when you work with nonlinear transformations, that you try to separate the aspect of the transformation that makes it nonlinear in a way that the remainder of the transformation is a linear transformation. And that is a matrix acting on that 3D vector, nothing more. And it's a simple matrix. It's a matrix that essentially is diagonal here. We can split things, because what you see is what this matrix does is two things. First of all, it removes the last component, multiplying it by zeros. That basically gets us from 4D homogeneous coordinates to 3D homogeneous coordinates. And the second thing it does is it scales x and y components by the focal lengths. And so we can separate these two aspects by saying kf times pi 0 being what's called a generic projection. That is a matrix which just removes the fourth component. It takes a 4D vector and just keeps the first three components. And a matrix kf that scales x and y with the focal lengths. So this is just introducing some notation, but it ends up being helpful. Why is that? Well, because this is a generic projection matrix, and this is a matrix that depends on the camera settings, the focal length being something that is intrinsic to the camera. And so now we can, as you see, we have the Z component still here, and that makes the whole mapping from 3D to 2D nonlinear. But now let's assume that that Z coordinate is essentially constant. That is an approximation. Basically what it means is that you assume that you're sufficiently far from the object you're looking at. So your camera is sufficiently far away in the sense that the Z coordinate, the distance from the camera of all points of your object, is essentially the same. And if we then call that distance lambda, then we have a mapping lambda times the 2D coordinates is kf times pi 0 times large x, the 3D coordinates. And so we see now we have a linear transformation from 3D to 2D because we've made the approximation that the Z coordinate is a constant lambda. That is an approximation, but let's stick with that for now. What we do now is we combine this perspective projection with the rigid body motion of the camera. So here we put everything together in one mapping from 3D world coordinates. Remember, x large, the large coordinates in my notation are always coordinates referring to 3D points. And x0 in particular refers to a 3D point in a world coordinate frame. So not in the camera coordinates, but in a coordinate system that is fixed to the world. So we have a point x0 that we're looking at, and now we do two things. We first transform that point, the 3D point, into a 3D point in camera coordinates. How do we do that? Rotation, translation. So there's a rotation and a translation that maps the world coordinate point into camera coordinates, as we've seen in the last class. In homogeneous coordinates, by appending the 1 here, we can, as you may recall, write this as a matrix transformation. So this matrix rotation translation 0, 1 acts on that homogeneous coordinate vector, where the last component is just 1. And that way we can say large x is that matrix we call little g times x0. And remember, that is an invertible matrix. This is the rigid body motions. So now we are in camera coordinates, and as you may recall, we get from the camera coordinates to the 2D coordinates by applying a generic projection pi 0 and this intrinsic parameter matrix that scales with the focal lengths. And so this is the transformation from a world coordinate vector x0 to a 2D vector x, where lambda, remember, is the distance from the camera. You see, we have a multiplication with this focal lengths, the matrix kf. In practice, you can actually neglect that. You can, and the issue is, once you have 2D coordinates, you're free to choose in what units you want to measure length. Remember, we can define lengths in terms of pixels, in terms of centimeters, meters, whatever, inches. You know, you can choose your units, and what you can do is you can say, I want to measure lengths in units of the focal lengths. How many focal lengths is it from one point to another? And if you measure lengths in terms of in units of the focal lengths, then that amounts to just, you can just drop the matrix kf here. And so then the projection is nothing but lambda x is pi 0 times x is pi 0 times rigid body motion times the world coordinate vector x0. And so you see there is the two effects that we have to get from world coordinates, 3D coordinates, to image coordinates, and that is a rigid body motion, G, and a projection matrix, pi 0. And so now we've written it in a very simple linear form, from world coordinates to camera coordinates, from camera coordinates to image coordinates. Typically, we will see a number of these matrices acting on some vector. The way you always have to read that, just to remind you, is you have to read it from right to left. We start in world coordinates. G gets us from world coordinates to the camera coordinates. Pi 0 does a projection on 2D, scaling with the focal lengths. Here's it written out a little more, and this is actually going not to image coordinates but to pixel coordinates. That is, so this may be confusing in the beginning. We have a number of different coordinate systems at this point. We have world coordinates, we have camera coordinates, 3D, then we have image coordinates, and then we have pixel coordinates. Maybe to write that down, the world coordinates, then we get the camera coordinates, then we get image coordinates, and pixel coordinates. Why should we distinguish that? Well, the camera coordinates are such that if I have an image here, there is the optical axis that typically goes through the center of the image, and so then this is my coordinate system in the camera. In the image coordinates, right? But if you read in a digital image, some of you may have done that in this or that class, you will typically recall that the center, the point 0, 0 is at the bottom left or bottom or top left. I mean, there's different ways to, but it's typically not in the middle of the image, because pixel coordinates are by definition positive, so there's no negative coordinates. That is a convention. It makes things simpler, but it means that if we have image coordinates that go from -1 to 1, -1 to 1, the pixel coordinates may go from 0 to 255, 255. That is the coordinates of each pixel. So there is a transformation that is taking place in the digital camera that basically assigns each point in the image plane a pixel coordinate. And that transformation can be modeled by such a matrix here. What this does is very simply OX and OY refer to the center of the image, where the optical axis is, in pixel coordinates. So that is exactly this offset that we have here of 0, 0 being shifted to the lower left corner. See, if we add this in the homogeneous coordinates, it creates just a translation. And then you have a scaling Sx and Sy. These two scale factors, they basically refer to the length scaling. I wrote it down. Where did I write it? Basically, this does the mapping from image coordinates to pixels. Yeah, that's the scaling in X and Y direction by Sx, Sy. What we sometimes have, but often neglect, is there is a skew factor that accounts for the fact that pixels in a real camera may not be perfectly rectangular. So there is a certain skew, but in most of what we'll do, we'll actually neglect that skew factor. We'll assume that it is near 0. So in this way, we have a transformation from a 3D coordinate vector in camera coordinates, x, y, z, projection onto 2D by the generic projection matrix, scaling by the focal lengths in x and y, and a transformation of these image coordinates to pixel coordinates. And we will call the pixel coordinates x prime, y prime 1. And always here there is the distance from the camera, lambda. Now, we have a lot of projection and a lot of matrices going from one coordinate frame to another. This is camera coordinates, this is going to image coordinates, and this is going to pixel coordinates then. But what is useful in separating the different matrices here is to look at which transformations are intrinsic to your specific camera. And here that is clearly the focal lengths. That depends on your camera settings, how you choose your focal lengths of your lens. For example, if you have a zoom lens, you can actually change, or you can change the focal settings in any camera. It basically tells you where in the world it focuses. It's not the zoom lens, sorry, it's just a focus. This is a camera intrinsic parameter. In addition, these parameters are also intrinsic to your camera, to the digital camera, and they can actually change. For example, in a digital camera, if you switch the resolution, say from 1 megapixel to 2, 5, 6, 8 megapixels, what is switched are these scale factors. They are changed. So the same point in the world will be then associated with different pixel coordinates depending on what resolution you chose. And so both of these matrices represent parameters that are intrinsic to your camera, and so the product of these two matrices, Ks times Kf, is called K, is called the intrinsic parameter matrix. Intrinsic in the sense that it only depends on your camera and the settings of your camera. It does not depend on where in the world your camera is.
Sorry, what is the difference between lambda and focal length?
Focal length is a setting of your camera. It depends on the lens. Lambda is the distance of the observed point from your camera.
Real distance or?
The real distance, yes. Is the z coordinate of our 3D points, essentially. In principle, indeed, this factor lambda is the same as z here. But if we work in the approximation that z is essentially constant for all points, and we can call this lambda. So the reason why this is not z but lambda is to basically show this approximation that we're working in a constant depth approximation. Yes, these parameters are intrinsic, and you may imagine, in addition, there are so-called extrinsic parameters. And in fact, if we combine this with the rigid body motion of the camera, then we see what we have is, so here's the matrix Ks, Kf, the intrinsic parameter matrix, that is the focal length times these scale factors, and here the skew factor, and then the offset from the center, Ox, Oy being the offset of our center, meaning the center of the image in pixel coordinates. And so this is the matrix K, and then the transformation from world 3D coordinates, 3D world coordinates to 2D pixel coordinates can be written as in this fashion. There is a projection matrix we call large pi, and it's made up of a rigid body motion acting on x0, bringing it to the camera coordinates x, then a generic projection pi 0 that maps to 2D, and then the intrinsic parameter matrix K. And so you see, this is called the intrinsic parameter matrix. The extrinsic parameters are in G, the rigid body motion. Extrinsic because in an image acquisition setting, you will typically try to fix the intrinsic parameters of your camera by fixing the focal lengths, etc., and not changing the resolution from one image to the next, but keeping everything fixed. And then all the degrees of freedom you have during the acquisition process is you can move the camera around. And these parameters associated with the camera motion, the rotation and the translation, they are called extrinsic parameters. which means you remember there's 6 degrees of freedom, modeling the extrinsic parameters, rotation and translation, and then in addition we have these intrinsic parameters. In a lot of 3D reconstruction problems from images, there is actually 2 different scenarios you have to separate. One is the case that you have a calibrated camera. That means you know the intrinsic parameters from some calibration process. Basically, you can, if you have your own camera, you can take it into your lab and you can take an object where you know the sizes, you can take images, and you can in that way determine focal lengths, or you can often specify them in the settings once you, before taking an image, you can set the focal lengths. That is a reconstruction problem which is somewhat easier. It means that we already know what K is. There is the so-called uncalibrated reconstruction. That is, you are given the images and you don't know what the camera was. You don't know what the focal length was. You don't know what these skew factors and the scale factors were. That is a little more nasty, to be honest. And typically, if you can, you should try to determine the camera parameters. But often when you do image reconstruction, say from images on the internet, and this is becoming more and more popular, people have devised techniques where you just, say, type in the word Notre Dame, and it just downloads images from the net automatically from Google or other, and then generates reconstructions, 3D models of Notre Dame. And to some extent, these techniques actually work. Meaning you can do image-based reconstruction without having a camera today. You know, the internet is full of images, just take those. There's enough of them. But what you often miss when you take images from the net is you don't know the intrinsic settings of your camera, and that makes the whole problem more difficult. Turns out, though, that even on the internet, a lot of the images will tell you the camera settings. So often people will not only store the image, but often a lot of image formats will automatically store the settings of the camera under which this image was taken. And so even if you download images from the net, sometimes you have the parameters. So you should often, before starting reconstruction, you should check, do we have access to the camera parameters? And ultimately you would want that, of course, because it simplifies life. So the only thing in a calibrated reconstruction that you don't have, that you lose, is the 3D point coordinates and the motion of the camera. And this is in fact what we will mostly focus on in this class, and I will talk a little bit about the uncalibrated setting towards the end. So this matrix, pi, we call it the general projection matrix. It basically combines both the rigid body motion of your camera and the perspective projection. So it's one large 3x4 matrix that contains, as you can see, translation, intrinsic parameters, and rotation and intrinsic parameters. Again, you should be careful. If we write things in this way, it looks like we have a linear transformation getting us from world coordinates to the pixel coordinates. But recall, strictly speaking, this transformation is not linear. We've just made it look linear. We still have the scale parameter. And that is the third component, the z coordinate. So in practice, you have to still divide by lambda being the third component, being the z coordinate. And so you can write the projection, the real projection from 3D world coordinates to pixel coordinates, x prime and y prime. You can write it in this fashion, where the pi's, pi 1 through pi 3, transpose are nothing but the rows of this projection matrix. 3 rows of the projection matrix. So the first is the x component, then divided by z, and the y component divided by the z component. And so here you see much more that this is not a linear transformation, that you have a numerator and a denominator. And then in pixel coordinates, in homogeneous coordinates, of course, the third component is just 1. Here, to summarize again the intrinsic parameter matrix, it looks like this: fsx, fsy, and fs theta, ox, oy, the offset of the origin. Just to recapitulate, ox and oy are the x-coordinate of the principal point. This is called the principal point, is the point in the image plane through which the optical axis, where the optical axis intersects the image plane. And so this is the pixel coordinates of the principal point in x and y pixel coordinates. Fsx, let's call it alpha x, is the size of unit lengths in horizontal pixels. So the unit lengths in the image, how many pixels are these in horizontal and how many in vertical? That is alpha y. And the ratio of alpha x over alpha y is called the aspect ratio, sometimes denoted as sigma. So you may have heard for images this notion of aspect ratio. And then, as I mentioned earlier, fs theta is the skew of the pixel. So it basically models the offset from rectangularity of the pixel. In practice, we assume it's close to 0. So we assume pixels are essentially rectangular, and then we don't have that off-diagonal element here.
Sorry, principal point is always in the middle of the image?
Typically, yes. But of course, I mean, this is up to slight variations. And depending on, you know, I suspect if you buy a very cheap camera, it may not be in the middle. You know, in a good camera, typically the principal point is in the middle of the image, but depending on how much money you spend, or possibly in a consumer camera, it's not exactly in the middle. And this is why then it doesn't matter whether it's in the middle or not, you can account for that by these offsets. Maybe one more comment. We talked about the standard perspective projection, which maps a 3D point to a plane. So again, here's our 3D object in front of the camera. And then here's the camera center. And as I said, we can represent the projection as the screen being in front of the camera center. In the reality, it's behind, but we flip the axis to bring it in front. But what we do is we project on a plane here. Alternatively, there's different projection models. There's a so-called spherical perspective projection, and that is the model that you have the same object. Here's the camera center. The rays go through the camera center, but then you assume there is a sphere of radius r, and that this is mapped to the sphere. And so you get another 2D image, but the points are on a sphere, not on a plane. We can model that transformation just as easily. It's not very complicated. What we typically do is we assume that this radius r is 1. So we have a length 1. So we, just like we say the distance to the screen here is 1, here we can assume the radius is 1. So we project onto a unit sphere in R3. And the projection of a point x in R3 onto a unit sphere can be written as x divided by norm x. Right? That gives you the same vector, but normalized to unit lengths, meaning it now lives on the sphere at that point. And so what that does is exactly, it takes a point large x, and then this point is x divided by norm x. It's on the unit sphere. We can do the transformation from the world coordinates to the pixel coordinates just the same way. So we have the world coordinate vector x0, a rigid body motion bringing it to camera coordinates, a generic projection pi 0 and k. And the only difference is, so we have exactly the same projection equation, the only difference is that now the scale factor, lambda, is not the length of the z coordinate, but the length of the entire vector, x. So that is square root of x squared plus y squared plus z squared, z squared. So you can see, whereas in the standard perspective projection we have a division by the z coordinate, the distance in z of that point, here we have, so the difference is that in the perspective projection onto a plane, what matters is the distance z here from the camera center, and here what matters is that length of this vector, that is x norm. And so the parameter lambda, the scalar factor here in the equation, is now the norm of the vector x. But essentially, you see the equation looks the same way. We have some scalar parameter acting on the 2D coordinate pixel vector, and then some linear transformation of the world coordinate vector. The linear transformation is exactly the same for the spherical projection. The only difference is that we have a different scale factor. And so we see that frequently, that up to that scale factor, x prime is nothing but a linear transformation of the world coordinates. And so often, to denote that, we introduce this tilde here to say x is the same as y up to some scalar factor, right? These are vectors, 2D vectors, or in homogeneous coordinates, they have 3 components, the third one being 1, and we say they're the same if they differ by a scale factor. And so, once we've introduced this notation, we can say the pixel coordinates are essentially a linear transformation of the world coordinates, where this symbol means the same up to scaling. One shouldn't be misled. What we do here more and more is we hide the nonlinearity in the notation. It basically tries to simplify the world that we see. The essence here is this linear transformation of the world coordinates, but there is a scale factor hidden in here. And that scale factor either depends on the z coordinate of the point or on the whole coordinate, on the length of that vector in the spherical projection. I talked about thin lenses, and there we had the pinhole camera model, the perspective projection. Once you have a real lens, for example, with a short focal setting, then things change a little bit. Then you get what's called radial distortion. And all cameras have some kind of radial distortion if they use real lenses. Often this radial distortion is neglected, but depending on what camera you have, what settings you work in, you may have a substantial distortion. So-called fisheye lenses create an extreme radial distortion. Here you see that this is a bookshelf captured with a standard lens, and their lines are essentially straight. And once you revert to a short focal length, you see the line that was straight in a regular lens all of a sudden is no longer straight. There is a distortion, and you can see that distortion increases towards the boundaries of the image. So that distortion increases with the radius. That's why it's called radial distortion. Right, so in the center of the camera, things are still nice, but then the further you move away from the center, from the optical center, the more distortion you get. One can calibrate that distortion. So if you want to do accurate reconstruction from images and you have a certain amount of radial distortion in your images, you may want to remove that. You want to undistort the image. Basically take the image and say, depending on how far I am from the optical center, I will try to take into account radial distortion and invert that process. And there are different ways to invert that process. To recapitulate this intrinsic parameter matrix K, it models linear distortions in the transformation to pixel coordinates, but these radial distortions are additional nonlinear transformation, nonlinear distortions. And that radial distortion is not always prominent, but it depends on what camera you have, and it depends on what settings you have. And in particular, if you take a wide field of view, so short focal lengths, and you have a cheap camera, then you will see substantial radial distortion. For example, often webcams create radial distortion. And you may have seen that when you do Skype with some friend and he or she has a cheap webcam, then sometimes the face looks different. When they go close up, the nose looks bigger, things look smaller. This is effects of radial distortion. In the modern digital world, we're often not so sensitive to things. We accept things, but there is distortion there. And you can actually model this distortion. A very effective model is this one. You say that XD and YD is the distorted point, and X and Y are the true coordinates of the point. And so you can say, see, this is already trying to invert the process, saying, I assume that the true X coordinate is the observed X coordinate, but then times some factor. And that factor is dependent on the radius. So there is a distortion that happens. The true X coordinate differs from the observed distorted one by the fact that it's multiplied with some scale, and the scale, as you can see, depends on the radius. And this is a model where you say I have a dependency that is square and fourth order in the radius, so that the R is the radius, meaning XD squared YD squared, the radius of the distorted point, and then A1 and A2 are parameters of my model. In particular, if you set A1, A2 to 0, you have no distortion. Then see, if you have A1 and A2 equals 0, then X is just XD is the same. But as soon as I have different parameters, it creates a certain distortion that increases the further away from the center I go. The larger R, so at R equals 0, I have no distortion, and the more I move away from my center, the more I get distortion. So this is a model that has two parameters, A1 and A2, and the way you can determine these is that you can take your camera, take a picture of a rectangular grid where you know where the points should be, and then you look at how is this grid distorted, and then you have a lot of points where you know where they should be. So you know the observed X and Y coordinate, and you know, because you know the pattern, you have the true X and Y coordinate, and then you can fit this two-parameter model to the data and determine the best parameters A1 and A2 that map all points to where they should go. So this is how you can estimate the parameters, and this is called calibrating the radial distortion. And then you can basically invert the radial distortion. In this fashion, you can just multiply all the X coordinates by this factor and the Y coordinates by the same factor, and that gives you the corrected coordinates. There's, of course, you know, everything, and this is typical in science, you can see a problem, you can propose a solution, and then later people will come and improve that solution. This is typically how science progresses. Here, for example, of course, if you have a model with 2 parameters and you have enough data, you can fit a higher order model. And this is a model that involves 4 parameters, actually 5 parameters, so it allows for what you just asked, is the center of the image really the optical center? Maybe not. And if it's not, then I want to correct for that. So we assume we have x coordinates, xd, so this is now vector notation. Xd contains both x and y. Then we assume there is some center. It may not be the origin. Sorry, there is some optical center. It may not be the center of the image, and C is then the location of the optical center, or the center where the distortion actually happens. So it may be that your lens doesn't just distort radially, but radially with respect to some other point. And that is this other point. So once I remove that other point, then I have a radial distortion by a function f that depends on r, and then I add that point again to correct for it. So that can happen. If you look at this image, it clearly seems that the center, the distortion is 0 here, and it grows towards the outside. But if you have a very cheap lens that was somehow manufactured in a cheap way, you may have a radial distortion that doesn't start at the center of the image, but somewhere else. And so you can model that, you can take that into account. This is a model proposed by Devernay and Faugeras in '95. And it has 5 parameters, A1, 2, 3, 4, and C. And here the R is, of course, then the distance with respect to that distortion center, C. And F is called the distortion correction factor. So this is the factor that says how much does the distortion increase the further I go away from the center of distortion. You can compute these parameters by looking at distortions of straight lines. So what you can actually do, if you have images from the net, you don't have the camera at hand, you cannot calibrate it, you cannot take images from some pattern that you know, but all you have are the images someone else acquired with it, and you can go back and say, give me the camera and let me figure out the parameters. If you don't have that, often you only have images. And still, let's say I give you this image and I say clearly there is a radial distortion, can you remove it? You can. The way you do that is that you make additional assumptions. And here the assumption would be, I assume that the bookshelves are straight. Whether that's a good assumption depends. I've seen bookshelves where the bookshelves themselves were not straight, right? But clearly, you know, if you don't have the camera, the problem is ill-posed. And then you have to make additional assumption. And so here the assumption is that you have straight lines, and that lines that you detect in the image that are slightly curved should actually be straight. And with that, you can then calibrate the radial distortion and remove it without actually having access to the camera. And that's been done, for example, by Zhang 96, Stein, Fitzgibbon 2001. So there's a number of approaches which have considered the aspect of radial distortion and said, can we do jointly 3D reconstruction from images and recover these distortion parameters? So this is a very uncalibrated setting, so to speak, where you often don't know the focal lengths, but you assume you don't even know what radial distortion you have. Now I will get to an aspect that is useful in the reconstruction. I said what we want to do is we want to recover the 3D structure of the world from images. And now we understand how images are projected onto the image plane. What helps in understanding or inverting the projection is to look at equivalence classes. as you see, once I project points onto the image plane, there's something that is lost. And what's lost is clearly the distance from the camera. That Z coordinate essentially is lost. We project to the image plane, and then the observed points have all unit Z coordinate. Basically, the Z coordinate is 1 in homogeneous coordinates, and so we have lost the distance from the camera, or the Z coordinate of these points, if you will. And the result is that clearly there is a whole family of points that give the same projection. So if I see a point in the image here, then there is a whole family, namely this entire line of points that correspond to the same observation, to the same projection. And that is important to understand what is the equivalence class of those points that basically are projected to the same location. It's useful because that limits the reconstruction accuracy. To know what are the possible 3D locations associated with the 2D point. And these possible 3D locations are called the pre-image of the point. So this is called pre-image. And it's useful because imagine I see the same 3D structure from a different camera now. And then I see the same point here somewhere. Then I have another pre-image, this one. For that camera, these are all points that are conceivable as 3D locations. And then you see the correct reconstruction is nothing but the intersection of the pre-images. And so one way to formalize reconstruction is compute for all points the pre-images, and for another camera, same thing, and then intersect the pre-images, and that will give you the 3D location. And so clearly, for this, the notion of pre-image is a useful notion to have an understanding what is a pre-image. It's all those points that project to the same 2D structure. And in fact, you can look at pre-images of points, but you can also look at pre-images of lines. Often when you do 3D reconstruction, you don't just identify points in an image, but you can identify lines in the image. So let's say I'm going to try to do a perspectively, so this is the image plane, a drawing, and then let's say I see a line here. Then there is a camera center here, and then I have a whole plane, basically this plane here, you can imagine, the plane which is such that when intersected with the image plane gives me the observed line. And so we can say the pre-image of that line on the image plane is that plane here. So this is the same concept. The way we can construct that is, let's look at a line in 3D. So this line we will call large x. It's going to consist of a base point x0, that's some point in the 3D world, always in homogeneous coordinates, and then some offset vector v scaled by mu. And if I take all real numbers for mu and weight them with v and add them to x0, that gives me all possible points on a line. So any line can be clearly written in this way, x0 plus mu times v. And if I'm working in homogeneous coordinates, the offset vector must have 0 in the last component, because the points should still be homogeneous coordinate points. So this is a line parameterized by a scalar mu. And then I can say, what does the image of this line look like? Again, we have the tilde here to denote this equality up to a scale factor, the depths. And we saw that there is a projection pi 0 of x. So we have pi 0 of x0 plus mu times pi 0 of times v. And what we see is all points x treated as vectors from the origin O to span a 2D subspace P. And the intersection of this plane P with the image plane gives the image of the line. So in my drawing here, this is the pre-image, it's called P, we call it P, and the intersection of P with the image plane is that observed line. So P is called the pre-image of the line. And so the definition of pre-image, the pre-image of a point or a line, is the largest set of 3D points that give rise to an image equal to the given point or line. So I see a point, and the pre-image of that point are all points that map to the same in the perspective projection. And the pre-image of a line is a plane such that the intersection of the plane with the image plane gives that line. Here's a visualization. I'm not so good at drawing, so I copied this from a textbook. Here is the line, the line in the image plane where I observe it. That plane here, and this extends infinitely, this is the so-called the pre-image to that line. And similarly, you can define pre-images for much more complicated objects on your screen. So you can define pre-images not just for points and lines, but in principle you can also say you see a curve and you want to say what is the pre-image of that curve. We will, in this class, however, focus on pre-images of points and lines because the pre-images are subspaces. See, this is a plane, is a linear space, and that tends to be helpful to work with linear spaces, whereas if you have a general curve in the image, then its pre-image is not going to be a linear space. And we can represent these linear spaces by the orthogonal complement. More specifically, a plane can be represented by a normal vector on the plane. I'm not very good at drawing, but I think maybe it's here. So if you have this plane here, you can define that plane by some normal vector. And that normal vector spans what's called the co-image of a point or a line. So you have the pre-image, all those points that give rise to this projection, and then you have the co-image, that is the orthogonal space to the pre-image. That is basically the normal vector on the plane. And so we can treat the image, the pre-image, and the co-image equivalently because they all determine each other, yes?
But the co-image has to be constrained somehow, right?
Exactly, yeah. Yeah, so you have to basically, if you have the normal vector on the plane, you have to define where the plane lies. Otherwise, that offset is free, yeah.
No, I mean like by the difference of the normal vector, because if the line isn't like the whole screen.
Oh yeah. Yeah. So you're referring to lines that start and end somewhere. What we consider here now is actually lines that extend infinitely, so that plane is also infinite. But you're quite right. In principle, I could consider line segments. Yeah. So here we consider lines that extend infinitely, because then we have that linear space. Otherwise, it's a space that has a boundary. And so we can say this is slightly confusing, I find, in the beginning, but you can say the image is nothing but the pre-image intersected with the image plane, right? So the image of that line is nothing but the pre-image intersected with the image plane. And so that's how you can get from the pre-image to the image, just by intersecting it with the image plane. The pre-image is the orthogonal complement of the co-image, so it's defined by that normal vector that characterizes this plane. The pre-image can also be written as the span of the image, right? The image are all points of the line. If I take any linear combination of vectors that define points on the line, then what I get is exactly that pre-image. And this is the same as this. Essentially, the co-image is the orthogonal complement of the pre-image. We saw that if we look at a line, its pre-image is a 2D subspace, and it can be characterized by a 1D co-image, the normal vector, basically the span of its normal vector defines the co-image. And all points of the pre-image, and hence all points of the image of L are orthogonal to L. So L is that normal vector that defines the plane. So all points on the plane are such that L transpose X is 0. That's what defines a normal vector. The space of all vectors, let's say we have a vector L, the normal vector on the pre-image. The space of all vectors is spanned by the rows of the vectors of L hat, the row vectors of L hat. Remember, L hat is the matrix that models the cross product. It is the matrix, it has rank 2. We saw it, it's the skew symmetric matrix that you can construct from L. It has 2 degrees of freedom, and they define this pre-image plane. We saw that earlier, L hat times L is 0, so that means all the rows of L hat are orthogonal to L. So interestingly here we can bring back this skew symmetric matrix hat, and the span of its row vectors is the pre-image P. That's for pre-images of lines. In the case that X is the image of a point P, so we have a point P, we see its image on the image plane, little x, then the pre-image is clearly a line. So for a point, the pre-image is a line, and the line can also be characterized by its co-image. The co-image, so the orthogonal complement to the line, is a plane. So you see there's a certain relations there. If I have a point, then the pre-image is a line, and it's in fact the span of that vector x. So I consider that point x as a vector, this vector here, and then the span of this vector, all scalar multiples of that vector define that pre-image, so span of x. And the co-image is similarly the span of x hat. X hat is the skew symmetric matrix, the rows of which are orthogonal to x. Because we remember x hat times x is the cross product of x with x is 0. So x hat times x is 0 means the rows are orthogonal to x, and that means they span the co-image. And similarly in a line, the pre-image is the span of L hat, as we saw here, and the co-image is the span of L. L being the normal vector on the pre-image. And so we saw that you can get the image itself by intersecting the pre-image with the image plane. That is, of course, true both for the point and for the line. If we intersect the pre-image of the line, the plane, with the image plane, we get the line, the image of the line, and similarly for the point. To summarize this class, there's a few minutes left. We studied perspective projection, and that models the transformation from 3D points to 2D points on the image plane. And in homogeneous coordinates, we have a transformation from a 4D vector to a 3D vector. And we saw there is different coordinate systems here. I've written it again. You have the 4D world coordinates. If you write things in homogeneous coordinates, then you have an element of SE3, this 4x4 rigid body motion, little g, that maps the 4D world coordinates to 4D camera coordinates. So 3D coordinates in homogeneous coordinates. And then we get from the 4D camera coordinates to the 3D image coordinates by a generic projection pi0 and the intrinsic parameter matrix, the scaling with the focal lengths. And then we have these skew factors and the offset and the scale factors that give us pixel coordinates. And we saw that these pixel coordinate transformations and the focal lengths scaling can be combined in what's called the intrinsic parameter matrix of the camera. And so in total we saw that we have a transformation from world coordinates to pixel coordinates, which does rigid body motion, generic projection, intrinsic parameter scaling. And in addition, I introduced briefly the notions of pre-image as being the maximal set of points which are consistent with some observed structure. And we can talk about pre-images of points as being the line of points in 3D that map to the same point. And we can talk about pre-images of lines as the plane that is mapped to the same line. Or, in principle, also pre-images of more general structures. But once we have lines or points, then the pre-images are linear spaces, and so then we can characterize these pre-images also by their co-image. And so we can use pre-image and co-image equivalently to using the image of the point, because we can recover one from the other. As you've seen, we can get the image from the pre-image just by intersecting the pre-image with the image plane. I added one slide, I think one or two slides, about projective geometry. This is a term, a field of mathematics that emerged from the study of perspective projection. And the idea, you've seen it, is that we work in homogeneous coordinates, so 3D points are represented by these vectors x, y, z, and 1, the last coordinate 1. But we saw that in the projection we often do not, we don't actually, it turns out we don't actually have to do this normalization that the last component is 1. One can treat, the problem is that this space is a little nasty. It's a 4-dimensional space, but the coordinates cannot be arbitrary. The last coordinate has to be 1. So to treat these representation mathematically is not as nice as having four independently, four degrees of freedom. And so what can be done is you can represent 3D points by a general vector in R4, an arbitrary vector in R4, where you take this vector and, let's say, scale it by a factor W. And then you can represent 3D points by 4 coordinates in R4, but you keep in mind that what matters about this 4D vector is only its direction. And so in that sense you can identify points in homogeneous coordinates with lines in R4 that go through the origin, because these lines, if you consider all possible scale factors W, in particular the 0, it means this is a line going through 0. If I consider it as a parameterized in W, this is a line in 4D going through the origin, and it represents the homogeneous coordinate vector here. And this is basically the idea of projective geometry, that you study this so-called projective space. So the projective space Pn is the set of all one-dimensional subspaces, lines to the origin, in the space Rn plus 1. So here we do P3 in our case would be the three-dimensional projective space, and it consists of all four-dimensional vectors that go, all four-dimensional lines in 4D that go through the origin. We are not actually going to use projective geometry in this class, but I wanted to give you a brief glimpse into it to show you what is the behind projective geometry. It actually starts with the homogeneous coordinates and then generalizes this in some fashion. Just if ever you hear about projective geometry, that at least you have some understanding what this is about. Okay, I'll stop here. Thank you very much.